The geometric distribution. Today we continue our discussion of random variables, but in our next two lessons we're going to be focusing on two very specific random variables that have special traits and special equations that help us understand them. So keep in mind we've been studying random variables where we've had expected values and variances and standard deviations. Okay. So under the umbrella of random variables, there are two very specific special ones called geometric distributions and binomial distributions. But they are still considered random variables. So everything we've learned up to this point still holds true for them. Okay? But these are just two very specific cases of random variables. So a geometric distribution is a special type of random variable with the following properties. In geometric distributions, there can only be two outcomes. We call them success and failure. Okay, so the situation has to be either or. You either make a shot or you miss it. You either call your mom or you don't. You either eat lunch or you don't. Like there's not a third option. Okay, so there's only two things that can happen. It's like a coin flip. Okay, one is success and one is failure. Number two, the probability of success, P, is constant. Okay, the letter P stands for the probability of success. Q stands for the probability of failure. And of course, to find the probability for Q, it's actually 1 minus P. So there are some textbooks that interchange these two. Okay, but the probability of that success is constant in a geometric distribution. So if you were shooting baskets where you could make it or miss it, and make it is success, your chance of making it has to be the same on every shot. Okay, so that P is constant. The third thing is that you need independence between trials. So one trial can't affect the next one. Okay, and that's related to option 2, where P is constant throughout the entire exercise. There needs to be independence between trials. And then number 4. N stands for the number of trials it takes to get our first success. Okay, so that's what a geometric distribution is. Okay, and this is important. You need to memorize this. The geometric distribution are the distribution of trials until you get a success. Okay, until you get a success. So you're going to shoot baskets until you make it. Whatever you're doing, the success you're looking for, you're going to do trials until it happens, and then you're done. So for instance, these are examples. Flip a coin until you get a head. So if you get a head on your first flip, you're already done. Okay, but if you get a tail on your first flip, then I need to flip again, and I keep flipping until I get a head. Roll a dice until you roll a 1, same concept. Shoot a basketball until you make it. Okay. So we're just waiting for that first success to occur. And part of what we'll be doing is predicting, when should we get that first success. Okay. Geometric distributions are skewed to the right, and I'm going to show you that in an example coming up here. So geometric distributions are not bell-shaped curves. Okay, that's not how these behave. And geometric distributions have expected values and standard deviations, just like random variables. Okay, and we can actually use our old random variable formulas to compute. So what we used to do with our calculators with 1-bar stats and putting the x as an L1 and the p of x as an L2, we can still do that, okay, with geometric distributions. All right, so if we were in class together, we would be doing an experiment on geometric distributions together by rolling dice. But since we're online, I did this experiment and I will just show you the results to save time. So the idea is we'll roll a 6-sided die until we roll a 1. Okay, rolling a 1 will be considered a success. So P would be rolling a 1. Okay. And then Q, failure, would be roll anything else. So 2 through 6 would be considered a failure. And we know that the chance of rolling a 1 on a 6-sided die would be 1/6, and the chance of not rolling a 1 would be 5/6. So that's one thing about geometric events. They are complementary, okay? That success and failure have to add up to 100%. So I did 100 trials of this. Okay, so I took a die and rolled it until I rolled a 1. Then I counted how many rolls it took, and then I did it again, and again, and again, 100 times. And I kept track of how many rolls it took me to get a 1. So I graphed the results in this histogram below. Notice it is very much skewed right. Okay, remember, distributions are skewed towards the tail. Okay, so I would expect my first success to happen pretty relatively early. Okay, I get most of my data, before the 7th roll. But obviously it took me a couple times where over 27 rolls for me to roll a 1. Okay, now obviously that doesn't happen very often, and the chance of that happening is very small. So that's why it's skewed to the right. And if I only did this experiment 100 times. If I'd have done it, let's say 1,000 times, we probably would have to extend this graph, because at some point I'm probably going to get it, maybe it'll take me 50 times eventually. And potentially, it could take me 1,000,000 times if I never roll a 1. Okay? Now, obviously, the chance of that happening is very slim, but that is one thing about geometric distributions. They are technically never ending. Okay? So what I did with those results after I graphed them is I took them and entered them into my calculator into L1. Okay, so if I got it on the 7th try, I put in a 7. If I got it on the 1st try, I put in a 1. So I put in all 100 numbers, and I did the one variable stats on L1. So I got the average number of rolls it took me was 6.15. Okay, so on average, it took me 6.15 rolls until I got a 1 for the first time. And then my standard deviation was about, if I round, it's about 6 rolls. So I'd expect, to get my first 1 somewhere between the 1st and 12th roll usually, right? And if you look on the graph, that would be this area of the graph. So most of the time, I'm going to get my 1 by then, okay? So we think about what that average stands for. It's actually called the expected value. So on average, it took me 6.15 rolls to roll a 1. Recall the mean of expected values. If I repeated this experiment many, many times, it would take me on average 6.15 rolls to get a 1. Obviously, I can't really get a 1 on the 6.15 rolls because you can only roll a die a whole number of times. But this would be the average of many tries. Okay. Now, I also made a table of my results from my 100 rolls. So you can see this table gets pretty long because, at one point it took me 32 rolls to get a 1, okay? Now all these percentages, because I did it 100 times, really stand for how many times, it actually happened. So like 20 times out of 100, I got it on the first roll, et cetera, et cetera. And then you can see there's a bunch, like I never got it, never took me 22, 23, 24, 25, or 26, or 27 rolls, okay? One time it took me 28, etc. Okay, you can see the probabilities are pretty high at the beginning, and then as you move to the right on the table, they get less and less, and that's because it was skewed right. So I took this table then, and I entered the x values into L1 and the p of x values into L2, just like we would with random variables, and then I did the one var stats L1 comma L2. Which is what we learned in the last unit. And these are my answers. I got 6.15 as the mean and 5.69 as the standard deviation. Those are exactly the same answers I got when I just put the raw data in and didn't put in the table. Okay, so either way, raw data or using the table, I got the same answers. And obviously this table might not necessarily stop right here, right? If I did more trials, this table would keep going, okay? And that's the thing about geometrics, is that technically they never end, okay? But the probabilities get so small as we move on that we would just ignore them, okay? So here's the cool thing about geometric distributions. I have some shortcut formulas for the mean and standard deviation that don't require me to enter everything into the calculator, okay? And these will be given to you on the AP exam on your formula sheets. So I have a formula for the expected value, which remember we call that the mean, and it's simply 1 over p. And remember, p is the probability of success. Okay, so to find the expected value, I would do 1 divided by 1/6, which is right here, which I circled, And if you divide that out, you get 6. Okay, so 6 is the actual expected value. We compare that to what we got in our experiment. We were really close, right? 6.15. And remember, the more trials I do, the closer my average should get to 6. Okay, you could call 6 in the blue circle the theoretical expected value. And you could call 6.15 the empirical, right? Because it's the result of an experiment. So just realize that. And then for the standard deviation, what I have to do is over here to the right, it's the square root of failure, remember Q is failure, over success squared. So remember failure, the chance of failing was 5/6, and the chance of success was 1/6. So I did that down towards the bottom. Okay, so I have 5/6 divided by 1/6 squared, and then take the square root, and we got 5.48. Again, that would be the theoretical standard deviation. And we can compare that to what we got in our experiment, and we were very close, okay? So in just 100 trials, we were able to estimate our values very, very closely, okay? So that shows you the power of an empirical situation where if you actually try something, you can get pretty close to the actual probabilities, expected values, standard deviations, etc. Okay? Now, we have some other situations that we can ask questions about. Instead of just, when would I get the first success and what's the standard deviation, I can ask questions like this. What's the probability that your first one happens on the third roll of the dice? Well, think of the 3 rolls, okay? I want to get my success on the third roll, which would have a 1/6 chance. But on the first 2 rolls, then, I couldn't get success, which means I had to fail. So those 2 rolls would be 5/6. Would be the chance of those 2 happening. So the chance of getting a 1 on the third roll would just be the product of those 3. Okay, which would be 25 over 6 to the third, which is 216, which ends up being about 11.5%, 11.6%. Okay. Well, we have a formula for this situation, and it's right here. So the probability of your first success happening on a certain trial is just failure for one less trial and then success. So using that formula, I would fail for 3 minus 1 tries, and then I would succeed. And 3 minus 1 is really 2. So it's the same formula, okay? I'm going to fail until I succeed. So if I want the first success on the third try, I have to fail for the first 2. And again, that ends up to be 0.116. Okay. Now, this calculation is built into your calculators. Okay. So if you go to distributions, and this is the picture on the right-hand side of the screen here, distributions is the same place that normal CDF used to be, or is, and inverse normal were. It's above the variables key on your calculator. And to find the geometric formulas, once you get to that distribution screen, if you actually arrow up, okay, the geometric formulas are at the bottom, the very bottom of the list, okay? So there's 2 formulas, and we'll talk about them both. The first one is called Geometrics PDF. So there's a P, and it's super important. And the P, the Geometric PDF, does this formula. It accomplishes finding your first success on a certain try. And all I need to know are 2 numbers, P and X. P is the probability of success, and X is when do I want that success to occur. Okay. So on my calculators, I would use the Geometric PDF command, and I would type in 1/6 for the probability of success and a 3 for when I want it. And if you do that calculation, you'll also get 0.116. Okay. And this is what it looks like on a TI-84. It'll ask you for the P, 1/6, and then when do you want it, a 3, and then you just click paste, and it will get you the answer. Okay. Again, remember, this has to be the PDF one, so be careful, because there's another one, Geometric CDF, and we'll talk about that next. Another question I could ask you is, what's the probability that your first one happens on or before the fifth trial? So on or before the fifth. Let's think about that for a second. I could get my first one on any of these rolls. And remember on the table, it actually went up to like 32, right? So if X was what trial do I get my success on, this question is asking, what's the chance of getting it on or before a certain trial? So on or before the fifth would mean all of these count, okay? Fifth or below. So we have a function on your calculator that will do this. So it'll figure out 5, 4, 3, 2, and 1 and add them all together. And that's geometric CDF. Okay, so this one's the C. Again, you're just going to type in two numbers. P is the probability of success. And the X is what trial do you want your success on or before. So if I want it on the fifth trial or less, I would type in a 5 and a 1/6. Okay, so if I go to my calculator, this is what you would type in, 1/6 and 5. And I get, by rounding, about 0.60, roughly. Okay, so there's about a 60% chance that you'll get it before, on your fifth or before trial, which makes sense because remember our expected value was we should get it by the sixth. So it should be pretty high chance that we'd get it by the fifth or before. Okay. All right. Now another kind of a fun formula you can look at is trying to find the probability of success after a certain trial. So I could ask for after the fifth. So this is the formula for after a certain trial. This one's not given to you on the AP exam, so I'm just going to show it to you quick. It's just failure to that trial. So on this problem, the chance of not getting a 6 is 5/6. And I want to know what's the chance I get it on after the fifth. So I do the 5/6 to the fifth. And I get 40%. Which makes sense, I think, if you think about it, because the chance of getting it on the fifth or before was 60%, right? So fifth or before is a 60% chance. After fifth would have to be 40%, because everything has to add up to 100%. So that's just kind of a fun formula. In practice, if they say after the fifth, what I would do is use the geometric CDF formula for 5 and below, and then subtract it from 1. Okay. Now, here is an example that I'd like to do with you using all of our formulas that we've learned. So the example says, suppose someone makes 70% of their free throws and assume free throws are independent. Okay, so I have to assume that they're independent, even though free throws might not be. You know, if you, depending on the time of the game you're shooting them, maybe you're more nervous, so they have a less chance of making it. Maybe if you make the first one, you're more confident on the second one, and if you miss the first one, you'd be less confident, but we will assume that they're independent, okay? And it's make or miss, right? Either make your free throw or miss it, so it's success and failure. We assume that your chance of making it's always 70%, and we're gonna look for the first missed free throw, apparently, okay? So when we expect our first miss? Now, the event we're waiting for is the success, okay? So I have the probability you make a free throw to be 70%, but that's not success in this problem. Success in this problem is missing because I'm looking for the first miss. So success in this problem, P, is 30%. Okay, so that's super important to understand. You wouldn't think of missing a free throw as being successful, but a success in geometric distributions is just the event we're looking for. Okay. So when would we expect our first missed free throw? That was just the expected value formula. So it'd be 1 over the chance of missing, which is 30%. So if you divide that on your calculator, 1 divided by 30% is 3.33. Okay. So what that means is we would expect our first miss to happen by the, a little more than 3 free throws on average. Now, can you really miss your 3 1/3 free throw? No. But if you had someone that made 70%, shoot free throws multiple times, okay, they would average their first miss on 3.33 attempts. Then the second question, what's the standard deviation of the first miss? That's this equation. And again, these will be given to you on the AP test. So remember that Q is failure, and in this case, a failure is actually making it. So that's 70%, and success was missing, and I need to square it. So we would do that on our calculator. And I would get 2.79 as my answer. Okay, so you'd average, you get your first miss by the 3.33 shot, and that will vary about 2.79 shots around that. So about 3 shots. So somewhere between your first free throw and your 6th, you should have your first miss if you make 70%. The next question is, what's the chance the first miss is on the 5th free throw? So if your first miss happens on number 5, that means that's the 30% chance. So that means I had to make it on the first 4. The chance of making it was 70% each time, right? So if you want to do it, it would be 70% to the 4th times 30%. And remember on your calculator, we do have a command for this one. Geometric PDF. The chance of missing it is 30, and I want to know what's the chance it happens on the 5th try. Either one of those will get you the correct answer. And I get 0.07, about a 7% chance. Okay, that's your first miss happens on the 5th one. And that's pretty small, but remember, you should have already missed by the 3rd shot. So the chance that the miss is on the 5th is a little smaller. The next question says, what's the chance the first miss is after the 5th free throw? So when they do these after the 5th, I like to just draw a quick list here of what's happening. After the 5th would be 6 and beyond. Okay. And we have a function on your calculator that'll get you 5 and below. So I would figure out 5 and below, and then I would subtract it from 1. So for 5 and below, that's geometric CDF, and I would type in 30% and 5. Okay, that's the chance I would miss it on the 5th or the 4th or the 3rd or the 2nd or the 1st. So that is 83% chance. Okay. But that's this number. I would like to know what's the chance it happens after that. So 6th, 7th, 8th, 9th, whatever. So that's the complement of that. So it'd be 1 minus 83% or 17%. Okay. And then last example, what is the chance the first miss is before the 4th free throw? So I'm going to use that same list. Before the 4th means 3, 2, or 1. Okay. Before the 4th means, the 4th is not included. So it's just 3 and below. So that would be geometric CDF 30% 3. And that'll include 3, 2, and 1 in my answer. Which is 0.657. Okay? And pay attention to rounding when you're typing your answers in to your homework. Usually you'll be asked to round to 2 decimal places, okay? All right, good luck with geometric distributions.